Hey guys, today we are going to talk about looking for patterns in different properties of stars. The benefit for us is that somebody, actually two people, have already kind of identified some of these patterns. And they formed what is called the Hertzsprung-Russell Diagram. Now the Hertzsprung-Russell Diagram, or the HR diagram for short, is something that shows us the pattern between stars. And this helps us kind of understand where they're at in their life cycle. It helps us understand where they're going. And all that helps us figure out how we can use this kind of information to understand stars. It helps us understand the sun, which is, of course, the closest star. And in understanding the sun, we can kind of understand the effect that the sun has on us. So, the first thing I want to talk about is how we plot variables. Plotting variables, let me change the color of my pen real quick. Plotting variables allows us to see patterns. So we plot variables to see patterns. Now, this particular one, I have a random distribution of variables. So there is no relationship here. Okay? There's no, it looks like they go kind of all over the place and they do all sorts of things. And that's okay. What we know is between quantity X and quantity Y, whatever it is, there is no pattern. And that helps us understand the way quantity X and quantity Y are related. Okay? Now, here's the trick about the Hertzsprung-Russell diagram that we need to keep in mind. Okay? This particular chart only plots two variables. However, it is possible to plot more than two variables. And the Hertzsprung-Russell diagram has more than two variables, so we have to keep that in mind. Now let's look at something that does indeed have a relationship. Okay, here's the relationship between mass of individuals and their height. And we notice that they kind of head in this upward direction. Okay, so there's a pattern here, and that's awesome. Okay, what this means is we kind of interpret that more height or more mass means more height under normal conditions. Okay, or more height means more mass. Now, of course, there are some exceptions to this. For instance, this person only weighs 40 kilograms, but he's 1.6 meters tall. 1.6 meters, if I recall, is right around the 5 foot mark, 5 foot 6 inches, somewhere in there. I'm doing that conversion in my head, so I could be wrong, but it's definitely more than 4 feet and it's less than 6 feet. Okay, so, and then this person is very tall and weighs a whole lot. So this pattern is not perfect, but it does give us the idea that these two things are related. And that's why we plot variables. Okay? And of course, this, I forgot to write more. And of course, this makes sense. Taller people are made up of more, who has very short legs apparently. There we go. Are made up of more stuff than shorter people. So it makes sense that they would weigh more. And that's what we do, is we kind of try to justify or explain the pattern in a way that makes sense. Now, of course, once again, there are exceptions, but we can generally predict that if somebody is a foot taller than somebody else, if one person is a foot taller than someone else, then they probably have more mass. Okay? Now, let's see what this has to do with stars. Okay, this is an example of the Hertzsprung-Russell diagram, and I actually accidentally cut off part of it, so I'm very sorry. Down here, you can't see it, but it says 1.5, 0, 0.3, 0.6, 0.8, 0.9, and then for some reason it goes to 2. Okay, so that's the color index. Color index. I'm sorry, my recorder cut that off for some reason. Now, there are several variables on a Hertzsprung-Russell diagram. For instance, there is absolute magnitude. Over here, there is luminosity. Up here, there is effective temperature. And down here, we've already seen that it's color. So there are 4 variables on a Hertzsprung-Russell diagram. But this helps us to see what is going on. For instance, luminosity is the brightness of the star, which, how bright does it look on Earth? Okay. I'm sorry, I got that backwards. It is not brightness. It is the energy given off by the star, which we consider to be a function of brightness. So the more luminous the star, the more energy it's giving off on Earth, or what we measure on Earth. This is not to say that a star can give off 0 energy. It's just to say that we kind of watch how much energy it gives off. Magnitude is the standard brightness. This is the one this is the reason I messed it up earlier. Okay, so for example, there are 2 stars. Okay, we have one that is this bright, and we have one that is this bright. Okay, but here's the thing. This one may be this first one may be closer, and this one may be farther away. So this second one will look less bright, even though it may actually be brighter. So we convert that to a standard brightness so that they're all on the same scale, regardless of how far away they are. Okay? So when I say something has a brightness of -2, what I'm saying is that it's very, very bright if it were 10 parsecs away from the Earth. If something has this absolute magnitude of 8, it is not very bright, despite the fact that... I'm sorry, hold on. My brain skipped a step. If it has a standard brightness of 8, it is not very bright compared to something with a negative brightness. Okay? And this is assuming they are all the same distance from Earth. Okay? So absolute magnitude is the standardized brightness, as if all the stars were the same distance from Earth. Then, of course, you have surface temperature up here at the top. And one thing I want to draw your attention to is that it starts at 4,000, then goes to the left to 30,000 instead of the other way around. Okay, so keep that in mind. Okay, we can't just assume that because it goes to the right, it's increasing. We have to be very, very careful about interpreting data on a chart. We have to read the graph very carefully. Okay. Then, of course, down here we have the color index, which we can kind of see the colors break up from blue all the way to red. Okay, which is a function of temperature, size, and mass, and things like that. So, just to clean this up a little, there we go. We can see we have absolute magnitude on this side and luminosity. We have increasing effective temperature going to the left, and we have the increasing color index. So, in reality, a Hertzsprung-Russell diagram measures brightness, it measures energy given off, it measures surface temperature, which is what we mean by effective temperature. And it measures color. So these are the four things that a Hertzsprung-Russell diagram actually measures. And sometimes these are on the same side. Sometimes these are on the same side. But we have to be sure to look at both sides of the graph. Okay? Now, the last thing I want to talk about is there are several patterns that show up. Okay? There are four main groups to, give me just a second. I just realized I might be able to move this up. Oh snap, look at me being awesome. Okay. So there are four main groups. There is the giant group, there is the supergiant group, there is the main sequence, and there is the white dwarfs. Because when Hertzsprung and Russell graphed these, they noticed that most stars fell down this main sequence. However, some stars, particularly larger stars, were grouped up here together. Okay? So, an average star, since this is where most of the stars gathered, okay, one thing that we theorize is that an average star will start here. And then its brightness will decrease. And as its brightness decreases, its temperature decreases. And as its temperature decreases, so does the energy given off. So we generally assume that an average star slides down the main sequence. Now our sun is here. It's a little over halfway through the main sequence, which means it's a little over halfway through its life cycle. Now, the general idea is that, and I'm going to change the color of my pen because it's very hard to see this. As we get down here, it's going to jump up to the giant phase, slide some more before it dies, and actually shoots down here to the white dwarf side. Okay? So, having the Hertzsprung-Russell diagram helps us kind of understand what happens to a star over the course of its life cycle. Supergiants, instead, and I'm going to change the color of my pen again, the supergiants slide this way. So that gives us the idea that Betelgeuse and Antares are actually towards the end of their life cycle because they're massive stars, whereas Rigel, which is part of the Orion constellation, is at the beginning of its life cycle. So the Hertzsprung-Russell diagram allows us to understand what's happening. So since I know the sun is in the middle / later part of its life cycle, I know that it's going to give off slightly more material in the form of coronal mass ejection, solar flares, etc. So that allows us to come up with plans to handle that because we know about how often they're going to happen. Okay? So understanding stars allows us to understand the way they're going to affect Earth. And that is why the Hertzsprung-Russell diagram is perhaps the most useful diagram in all of science. Okay? Now, if you have any questions, feel free to leave them below in the comments, or you can email me. And, or of course, you can always bring them up in class. So I hope you learned a lot, and I hope you have a great day.